It's now my pleasure to invite Robert Schlögl from the Fritz-Haber-Institut in Berlin, who's going to tell us about Operando Spectro-Microscopy. Robert.
Good afternoon, everyone. I was thinking that we would hear such a kind of speech that you just gave as our master of ceremony, and I decided, nah, you should not try to repeat this because that's going to fail. But I'm extremely grateful that I'm here. I'm one of the old guys with John Thomas because I was in the Cambridge period with him. And I very much enjoyed everything that you said. John really changed my scientific life because after I had left Cambridge, I was completely convinced that Operando Catalysis, it's called today, is the future job. And I spent essentially all of my efforts in trying to develop methodology. And I also learned from John that it is super important to develop new methods if you want to make new discoveries. And also that he really deeply sunk into my scientific activity. So I can only underline and endorse everything that you said about John. And the fact that so many people are here and there's also family here shows very clearly how influential he was. So we will for a long time not forget him. But I know also that John was always interested in details. So yeah, the whole time I knew him, send me this slide, send me that data, send me this. So I decided I will not give a broad overview talk, but I go into significant detail. This is a non-didactical talk about catalysis. This is from expert to experts. So if I'm too deep into details, then this is not meant that I understand. One should not be so deep, but this is really a tribute to John because he really wanted to know everything to the last detail. So it was not good enough that you showed him a spectrum. He wanted to know all the little details. This is what we do now. What we learn about catalysts from Operando analysis. He could have had this title, but he would have had a much more eloquent way of putting it. This is clear. So before I go into these deep details, I would like to thank everybody who contributed to this. And this, of course, first my group. The people who are written there by names are the group leaders that coordinate this whole activity. And there's a whole lot of people who are organized in certain teams, and these teams are indicated here. So I will report a little bit about electrochemistry. I will talk about dry reforming of methane, and I will talk a little bit about nickel as a general element. Also knowing that John was quite active on nickel. There are external groups with whom we collaborate. That is also quite important. I will not mention them. And there is in particular one recent large project that we initiated in Berlin that is going to be possibly the nucleus of catalysis science in Berlin in the next 10 years. This is CatLab, and there are some important people who run the show there. Now, one teaser first, Operando analysis uncovers active sites. So static active sites, active sites are these elusive things that do everything, but we are not so exactly sure how they look like, because at least I have never seen an active site being active. I just know that there are such sites. And there are irregularities in interfaces that activate reactions. At low reactivity, they prevail during observation times suitable for structural analysis. This is why we think we understand where the atoms are. Unfortunately, under performance conditions, that is not true, and this is the reason why there is this elusive gap in catalysis science between real catalysis and physical chemistry or model catalysis. And the reason for that is that the catalyst material begins to react with its reactions and forms a unique, at least termination layer on a stabilized support. So the material completely transforms. And this is the very reason why John knew this already from the beginning. And this is why he introduced this idea that you need to do Operando, what he called at the time in situ analysis, because only then you would recognize this. The layer fluctuates in composition and structure driven by phase transitions induced by the chemical potential, because a working catalyst is metastable with respect to its preform when it's there at room temperature and at atmospheric conditions. And the fluctuations regenerate high energy sites identified as the nucleation sites of the phase transition. So all what we are talking about is we are having a material that is about to undergo a phase transition, and in this process of about, it creates this high highly active sites. And the art of it is that the material must not complete the phase transition. This is the reason why we call it frustrated. And what frustrates the phase transition is, of course, the catalytic reaction by itself. This is the reason why it is not being completed. Now, this gives a wealth of chemistry. So this little table tells you what can happen if you give any of these 4 reagents, and then you see what kind of material transformations you get. And whoever does analysis of a working catalyst finds this enormous complexity of things that are quite different from what you had actually put at the beginning in the reactor. But this is absolutely normal. This is to be expected as that way. An example for that, ethylene epoxidation, also one of John Thomas's early things. In the Cambridge days, there was quite a lot of activity about this reaction, and it was at that time enigmatic, and I will tell you now in one slide why this is still enigmatic. So in order to make ethylene epoxide from ethylene, you need electrophilic oxygen, a special form of oxygen atoms, and that's another take-home message that we also learned from John already. It's not just oxygen atoms, there are many different types of oxygen atoms, so O2 minus is not enough. And this is limited by the coexistence of oxides and nucleophilic oxygen. So they are the enemies because they are CH activating, and if you have CH activation, active oxygen, you get at least combustion or other oxide formation. The kinetics of something that you all who are familiar with this know this word very well. Oxometallar cycle prefers the acetaldehyde because it's thermodynamically the preferred reaction, is not ethylene epoxide. I will show in a moment what the oxometallar cycle is. And the subsurface species, the nucleophilic species, has a very strange by-effect that was not discovered until recently, because it goes into material and it segregates a few sulfur atoms to the surface. And these sulfur atoms are ubiquitous in all kind of, almost in all kinds of transition metals, but definitely in all coin metals. And this forms a submonolayer of sulfoxide, and this sulfoxide produces the electrophilic oxygen. So it is a dirt that comes from the material, the silver catalyst, that actually does the job, and not the silver by itself. And only this leads to the energetically non-preferred ethylene epoxide. Now, where's the evidence? So what you see there is the traditional way of looking at it. You form this oxometallar cycle. You see it on top. This is this little diagram where you see the ethylene and the oxygen atom. And with limited activation energy, you form the thermodynamically stable acetaldehyde. This is at the bottom. And the barrier to form ethylene epoxide, and of course the energy gain that you get from ethylene epoxide, is against this. And this is the reason if you have naked silver, the productivity of ethylene epoxide is very low. You get a little bit, but most of it is just combustion. This changes completely if you go to reaction conditions where the oxygen is not only at the surface, but also underneath the surface. Because as I said, as a consequence of this, a few sulfur atoms come to the surface. And this is only a few atoms. You need super high sensitive detection method to find this. And there are literally thousands of papers who did photo emission on the silver surface, and they all didn't find the sulfur, including ourselves. We also didn't find it until recently. You know, the trick of this is that then you form this intermediate that you find. This is also an oxometallar cycle with a sulfur atom in between, this number 3, which you find on this diagram. This is the intermediate, and from there you have a very simple way to go to ethylene epoxide, because you can form a radical from this. You have a radical transition state, and of course, from a radical transition state, ethylene epoxide is way more easily formed than if you have nucleophilic oxygen, which does CH rearrangement. Now you can say, this is all theory, this is fine, you can compute this. Where's the evidence for this? The evidence comes from the middle part. This is an Operando experiment, which we do while the system is forming ethylene epoxide. And at a certain point where this dashed line is, we switch off the oxygen and we let the ethylene continuing. Then what you see immediately are two things. First, of course, if soon as the oxygen is being switched off, there's also no more ethylene absorbed from the gas phase. The oxygen is a prerequisite that ethylene absorbs on silver. And you see in this red line that the ethylene epoxide is decaying, which you would expect because there's no more oxygen. But exactly simultaneously to this, also the sulfur is disappearing. And the sulfur is not dissolving, but the sulfur is dissolving as elemental sulfur back into the silver because it's reduced by ethylene. And this is why if you wouldn't do Operando analysis, you would never ever find this, because when you take the silver material before and after the reaction, there's absolutely no sulfur to be seen. It's only there under reaction conditions. And this is a very nice resolution of a secret. It works. And we can now dose sulfur to this, and then we see that the productivity is increasing. And when you look at this structure, then you also understand what this elusive rhenium promoter does from shell. It's exactly the same thing. It forms, instead of sulfoxide, this rhenium oxo analogous to that. That's the reason why it works so fine. We go back to the general things. What we learn is formation and the abundance of active sites depend on the local chemical potential. Oh, that's way bad. This is the reason why UHV studies of catalysts are a waste of time, because there's no chemical potential. So this is not what you want. Unfortunately, there's a feedback loop to the reactivity of the active phase, because the active phase is formed by the reactions. So if you change that, then of course you change the structure of the system. And that's even worse, because then, of course, the transport of mass and energy come in this, because they also change the chemical potential. Clear. This is why you cannot study a catalyst without considering the reactor and the flow conditions and all of these things that we know very well from practical life. This is natural and to be expected. Transport is controlled by meso and macro structure plus the reactor setup. This is where chemical engineering has its field to go. And this is not something with a technical detail. This is absolutely critical to the operation of a catalyst. So those who are practicing this know this, but in some areas of academic science, this is not so well recognized. The reactivity is related to the kinetics of the phase formation, depending on the nanostructure and the morphology, because of course there's also a kinetic aspect to this. The response of a catalyst to its local chemical potential depends on kinetics, not on thermodynamics. And this is where all this black magic comes in. So how do you do this exactly, and how dirty is this, and how many impurities are in the material? This comes from there. Now, this is the final slide, I would say, of my presentation, but I'm having some more senses. But I do this that we begin all to understand how complicated and involved the whole story is. What we make is the pre-catalyst, and we think about electronic structure and design and God knows what, and we think about transport. And everything of this beautiful pre-catalyst falls to pieces as soon as this pre-catalyst sees the first reagents. Then it transforms itself. You have seen this also in the slide before. And the consequence of this is restructuring and the reaction with the reagents, and then comes the activated catalyst. Now, the activated catalyst still interacts with reagents and undergoes, of course, its transformation. And this is this frustrated phase transition that you see. And the frustrated phase transition has now two outcomes. Either products are being formed, they unfortunately in another feedback loop change the chemical potential, or the frustrated phase transition is not frustrated but completed and catalyst is deactivated. And the ratio between this red and this white arrow determines the lifetime of the catalyst. And we have two types of catalyst, one which undergoes a complete phase transition, and another type of catalyst where some components of the catalyst are segregating to the surface and forming their termination layer. So these are two different types. But the story is always the same. So you see these two feedback loops, and the art is to bring these two feedback loops to a maximum overlap, because then you have the maximum performance of the system. But if you don't know all of this, of course, you cannot optimize this. So designing a catalyst is a way more complicated thing than having an optimized electronic structure of the pre-catalyst. That's of course necessary, but it's only half of the story. So this is the rest of the talk. What can we see there? We go to electrochemistry and do a little bit on iridium. Iridium is very well known. It's good for oxygen evolution reaction. And the operando analysis in the literature focus on the metal of the iridium, and the statement is with lots of hard action methods, it was found that there's a high oxidation state necessary that this thing works. A chemist does not like this, because we know heavy atoms or heavy elements in the periodic table do not like to have stable high oxidation states. So you think, as physicists are happy with iridium 5+ and 6+, but chemists think, it's probably not right. So we have to do something else, and this is why we decided we look not to the iridium, but we look to the oxygen of the iridium oxide. Maybe the secret is in the oxygen part, the ligand. And this is also in many cases in catalysis science overlooked. Of course, ligands are super important. This is not just something around the central atom. This is a very important component. I think John was a master in understanding this. So his idea about single-site catalysis is very much driven by this idea. So we need nexus, unfortunately, because Fourier emission, as I will show you later, is too insensitive to that. And then so we will see, can we identify something that is unusual? Yes, we can identify it. There's an oxygen radical center involved in the iridium oxide that you would normally not expect. And this is not iridium oxide like rutile, that is the active phase, like we had it in the silver, but it is a defective iridium oxyhydroxide species that comes from the hydrolysis of this rutile pre-catalyst. So what you put on the electrode is rutile, that is, as I said, the pre-catalyst. Now we discovered this with a method, this is an old slide, that is electron energy loss spectroscopy. And also John was he was extremely keen on saying we use electrons and electron energy loss spectroscopy to discover locally defined details of the electronic structure. At the time where John was trying to do this, that was impossible because we didn't have the proper microscopes. But now we have these microscopes and we can do such kind of spectroscopy. We can do this, of course, later than on synchrotrons, like next door. And we synthesize this defective iridium oxides that had this feature in it. And then, of course, the question is, how do you know that this is a radical? Again, the theory helps a lot. This was done with Frank Nese together. We did quite a bit of calculations in order to find where this radical structure sits. And as it is always in covalent situations, some of this extra charge is on the oxygen and some is on the iridium. So when you look at the iridium, you see a change at the iridium. When you look at the oxygen, you also see a change. But of course, you need to look at both simultaneously to understand what this is doing. And this fight about the shortened iridium-oxygen bond is perfectly fine from excess, but that doesn't mean it's iridium 5+. So how operando is this? This is also a typically Sir John question. He would have asked me this many times, but I showed it to him when he was still alive. So an operando experiment requires the simultaneous detection of the spectrum and the oxygen gas being formed, because only then you believe it. If it's only current that is flowing, this can flow anywhere. So you have to measure this, and this is not exactly simple. We invented 3 methods how you can do operando analysis in a liquid electrolyte interface with electrons of low kinetic energy. And they have pros and cons. I have no time to go into that. I just want to show you there's a whole catalog of possibilities. And here's the experiment. We take any one of these electrodes, and then we apply in blue potential pulse. Then we get a current response in green, and in red you see the oxygen that's being formed. So this is evidently clear. This is an operando experiment. Now, as we have this possibility, we can now ask the question, which of the many species of oxygen that are in the system are the relevant ones? And that is done also very quickly. Again, theory helps a lot because we had theoreticians that pre-calculated the to-be expected spectrum before we did the experiment, which is a very useful thing to do. And they learned us that this terminal oxygen that would convert itself into this radical oxyl species has a very strong next spectrum resonance. If it is deprotonated, it's really oxyl, but as soon as you protonate it, of course, the radical character disappears and the intensity of the nexus also disappears. That you see where it's written partly protonated, you don't see the spectrum anymore. This gives us the possibility now to do a real operando experiment. In the top trace, you see we change the potential upward, downward. Then we get, of course, a current flow. And in the middle and in the lower panels, you see the intensity distribution of the double coordinated terminal oxygen and the single coordinated oxygen at the surface. The green one is the single coordinated one. And when you look at the first derivative, then you find exactly the rate of the formation of the single coordinated deprotonated species is coinciding with the oxygen evolution reaction. That's the active side. This, I think, is a pretty good proof that we have now understood what that actually is. Now, why is this necessary? I have to rush. This is also John Thomas first. So I learned this really from him, looking at not at the crystal structure by crystallographic means, by function. And when you look at iridium oxide and you start with this fluffy iridium oxyhydroxide, then one learns that the important thing is dimers of octahedra of iridium. And if you think that the terminal transition is to form rutile because it is thermodynamically stable form, then one understands that these dimers, they have to move in order to create the rutile structure. And as they are moving, they are, of course, breaking up their linkages. And when they are breaking up the linkages, they change the oxygen content of the system. And this is exactly the reason where the oxygen evolution reaction becomes an active site, because there's a coordination site where water can be coordinated. And that's the way how that works. So this is a detail, we don't need this, but we can ask the interesting question, is this unique to iridium? Or is this a general way how oxygen evolution reaction works? So we go to nickel, and we stay with the rest of the presentation with nickel. This is another example of the oxidation of a covalent MO bond where M and O is oxidized. And this is not just M or O. So we do the same story and we make this nickel oxyhydroxide that is copy-paste the same chemistry that you find with iridium. It's a little bit more involved, it's more difficult, but in the end you get the same thing. You get this beautiful needles. It's a very reactive electrode. And you know, the alkaline electrolyzers that you have in large operation, they have exactly this as the active site on the oxygen evolution reaction. So what we see is very nice. In the next graph, we see exactly the same feature. This is this little blip that you find. As soon as you do in Operando, you increase the potential where oxygen evolution sets in. We see also our oxyl species. Oh, it's very nice. So we like this. This is really the same thing. Now the question is, this is really related to this change between nickel oxyhydroxide and oxyl. And for that, we do pulse experiments. And then, of course, if this is the active site, then the species that is our active site should follow in its concentration exactly when we change the potential. And you can see as a function of time, it does this perfectly. So if there's a potential low, then we have nickel 2 plus. This is this red curve. If the potential is high, then we have what people call nickel 3 plus, which is the oxygen plus the oxyl. And you see in green, this is the intensity of the oxyl species. So that fits very nicely. There are lots of details in this picture that we do not quite understand because this fine structure is not noise. This is kinetics. And when you change the nickel oxyhydroxide, then you change also this fine structure. So there is still quite a bit more in this, but I have no time to go into this. And we also haven't fully understood what we see here. So we go dig a little bit deeper into this transformation. We take nickel oxide, make a thin electrode on conducting silicon, and then we oxidize this and form nickel oxide. And when you do first the analysis and do this in dry oxygen, you find this get these blisters, and these blisters are there because this is a mixture of NiO and Ni2O3. So there's two phases being formed. If I put steam on this, these blisters disappear immediately, as you can see from the total right-hand picture. It's absolutely flat because water somehow mixes these two structures in such a way that they disappear. Now you would think, this is now homogeneous, but this is far away. This is not homogeneous whatsoever. For that, you need now photo emission spectroscopy and do this in Operando. This is now oxygen 1s photo emission. We do the same experiment. We do it with two depth resolutions. On the left-hand side, you see surface-sensitive photo emission. On the right-hand side, you see not surface-sensitive photo emission, so a little bit more bulk. And now you see lots of different oxygen species. Now, first, of course, the physicists are saying, Schlögl, you're crazy. So many lines. How can you fit so many lines into this broad spectrum? Simply because we spent about 3 years of analyzing all of the intensities of these three by doing chemical transformations. I show you in the next slide how we do this. So we are sure they're all correct. They're all real. And the interesting thing is into X-ray diffraction on this film is nickel oxide. And you see only nickel oxide. This is also what you would expect. But with Operando photo emission, you see barely any nickel oxide. The nickel oxide is this top right red little peak that you see. This is nickel oxide. The predominant thing that you see is nickel hydroxide. Yeah, we understand this now because this nickel oxide is hydrolyzed in the electrolytes. It's strongly alkaline. It's pH 13. This is the reason why nickel oxide doesn't exist under these conditions. That's normal. And there are a lot of additional features not so important to discuss this here. I just want to show you, my goodness, this is quite involved and relatively complicated. Now we change gears. We stay with nickel, we stay with oxygen, but we change the reaction. We go to gas phase chemistry. We do now CO2 reaction with methane. That is also an interesting thing. Also, John loved this reaction. We discussed several times what one can do about this, because that removes CO2 and makes synthesis gas. This is a very nice reaction. Unfortunately, this is way more complicated than you think, because there's a huge reaction network behind this. And what you observe when you do this practically, then you find that the products, the distribution between CO and hydrogen is variable in time. I say, how can that be? One reaction and you have a change in the product selectivity. That's interesting. Of course, the answer of that is it's not a single reaction. And this is problematic because it leads to deactivation of the nickel catalyst, which then forces you to put a lot of water in this, and then it's not a dry reforming anymore if you have to put steam in this. So that is not what you want. I show you here only how many reactions are involved. So these are the elementary processes, not the elementary, these are the individual processes that constitute this reaction network. And you see, this is endothermic and exothermic likewise. So, oh, this is interesting. So you can expect many different things to happen. In the next slide, I will show you. They do. So one thing that we can do when we do Operando analysis is we can also determine kinetic parameters inside the microscope. That means from the very surface that we are watching, we also get the kinetic parameters. And we observe two interesting things. When you look the Arrhenius plot for the hydrogen formation, then you see this is perfectly fine. It's spot on, like it's described in the literature. So we should be all happy about this. And the interesting thing is, it doesn't matter if you heat up the catalyst or cool it down, which of course we never should have a difference. When you look at the CO, however, that's very different, because A, you get different values, and B, it depends your activation energy, whether you heat the catalyst or whether you cool the catalyst. That has two implications. First, there are at least two different sites that are responsible for hydrogen CO formation. And in the CO formation, apparently there's a diffusion part involved, because this is the reason why there's hysteresis in this. So this is not only a surface process, there's also some bulk involved. Enough to do this in a little bit more detail. Now I show you two videos. This is a nickel catalyst, and the first one is during activation. And I want you to observe, please, the temperature. We always feed constant amount of power to this catalyst, and then watch the temperature and watch what you can see there. This takes about half a minute or so, so please take the attention and look at the many different things that you see there. This broad structure that you can recognize is the grain structure, and these grains have different orientations, and this different orientation should also have different reactivities. And this comes and goes, and this is quite interesting. What is this white stuff? I will show you in another slide what that is. This is not so easy to find this out immediately. And you would think now nothing happens. No, it comes again. Lots of things do happen here. And you see also that sometimes there's such a flickering on the surface. This flickering means that the conductivity of the surface is changing. And I can already tell you, this is the reason there's a segregation of silicon oxide. That is, can you remember the same story with silver in sulfur and silver? Here it is silicon in nickel. It's the same story. So it is oxygen is coming under, goes subsurface and presses the silicon atoms to the surface. Now, when you do this much later, you let this thing run for about a week. And the other slide, first I show you really that there's silicon oxide. This is now operando photo emission. We do now operando photo emission for the same time under the same condition on the same surface. And then we see quite nicely there's nickel oxide. Yes, and this is disappearing by the time. And there's a defective form of nickel oxide being formed. And there's a significant amount of silicon oxide being formed at the surface. So this is far away from nickel metal. But you buy nickel metal. This is a nickel foam catalyst that is also commercially available. It's only nickel by extra diffraction. Again, it's only nickel. Nothing wrong with this. Now, as I say, if you let this run for about a week, then you see the next video. And when you then look at the temperature, then you see it's rock on, totally stable. That's working perfectly fine. But now you have a blinking catalyst. So it's light, bright, dark, light, dark. You see also that the roughness of this is exactly the same position. The roughness has completely changed. This is this reconstruction thing that I also had in my slide, because the continuous operation of surface and subsurface transition restructures the whole thing in a dimension that you can see this with a scanning microscope. You don't need a TM for it. So, okay, long story. We can stop this. It blinks very nicely. And what we learn from here is when we take the derivative of the total intensity of this picture and look simultaneously at the product distribution, then we see there's always a change in the rate of formation of CO and hydrogen when there's a change in intensity of the picture. So this is apparently also related. We see something of the active sites. But what is that in detail? We need to do now a little bit of material science. The first and surprising thing is the CO2 is an oxidant to nickel. So nickel metal is completely oxidized by CO2. You would not expect this. You would say it's adsorbed. And the CO is completely dissolving. There's no carbon at the surface. So there's no problem with this. How do I'm doing in time? Not so well, huh? Should come to an end. I have 5 more slides. Is this okay? Fine. When we do simultaneously the oxygen spectrum, then we find again something extremely interesting. We begin with hydrogen activation because we clean the nickel. And what happens then is, again, silicon comes to the surface because hydrogen dissolves the nickel and presses out silicon. And then later, when we put the CO2 on it, then we see that a second liner comes. This is nickel oxide. But this is way more complicated than just simple nickel oxide. We know this from the previous work. This is only to remind you, be careful with analyzing this nickel spectra. There's a lot of literature with strange ideas about nickel 2+ and nickel 3+. That's wrong because this nickel 2+ spectrum has 2 components in it. So there's a ligand-derived photo emission and there's a central atom-derived photo emission, and they have a certain intensity ratio that depends essentially on the covalency of the nickel-oxygen bond. And this has nothing to do with nickel 2+ and 3+. It's very different. Now we do some test experiments. You see now Operando experiments back and forth, and the nickel spectrum is almost not informative. You see hardly any change, but you see massive changes in the oxygen spectrum when you heat it up and cool it down again. This is what you would expect because this is defect formation. You can now fit in with this data. This is one of the reasons how we do this fit. So we take this from this well-defined Operando experiments and extract the line shapes, and then we can do the fitting of our other Operando experiments where we do the dry reforming experiment. But we can also do something else. We can go to a focused ion beam and just cut a little cut out of this, where one of these blisters was that you saw, these white things. And then we look inside with the transition electron microscope, and then we find indeed the white stuff is nickel oxide. We would have expected this. And the gray dark stuff is metallic nickel, but in between, and that is also something that coincides now nicely with our photo emission, there's a nickel defective oxide. This is a layered suboxide. This is nickel O1 minus X, and this has a very complicated structure. It has nothing to do with rock salt of nickel oxide. And there's a reaction front that is between the metal and the nickel oxide. They are not sitting side by side, but they have an intermediate phase in between that is metastable. If you cool this down to room temperature, it's all gone. So a little bit about theory. Now we asked our question, how do we analyze this data? This is apparently nickel oxide is way more complicated than nickel 2 plus and O2 minus. Otherwise, you wouldn't be able to understand the complexity of the spectrum that we see. So we did a little bit of theory, and we introduced some defects. And the interesting thing is, in both cases, even if we remove nickel or if we remove oxygen, we strongly change the nickel-oxygen interaction. This is clear because the system locally responds to the missing atom, and this leads to a change of covalency. You can very nicely see from this color map that the electron density between the atoms drastically changes. And this drastic change, of course, is reflected in the valence band spectrum. You see in top a measured valence band spectrum, and in bottom you see the simulations of this. And again, theory is very powerful because it tells us where are the oxygen 2p states and where are the nickel 3d states. And we see now quite nicely there where the change is. This is where the oxygen 2p states are changing. Now it is unbelievable, and this is also not right, from core level spectroscopy, we know that the amount of oxygen is not changing as much as you would expect from this gray shaded area in the valence band spectrum. The reason why this change in the valence band spectrum is so big, because unfortunately the transition matrix element of the photo emission also changes when you change the covalency. So this is a very good indication. You have to be very careful with looking at the intensity distribution of photo emission if you change the local chemical bond. That is written in all textbooks of photo emission, but this is usually not taken into consideration when you do this analysis. Reaction network. This is now experiments. This is electron microscopy at atmospheric pressure. That is our latest achievement. We have now a transmission electron microscope and a scanning electron microscope that work at atmospheric pressure in a flow reactor arrangement. So we can now do no longer near ambient, this is real ambient. And you see the oscillations again for time reasons. You can believe me, this is beautiful. This is isothermal. So this is really kinetic oscillations. And they give us now a very interesting possibility to try to understand how the reaction works. These are our key reactions. The CO2 we have proven reacts to nickel oxide, and the nickel oxide is necessary to activate methane. Methane does not react with nickel metal. It only reacts with nickel oxide. That is also a myth that is in the literature. Whenever you look at this, then you always find you can only get methane activated on nickel metal if there's an impurity of oxygen. And this, if it is absolutely clean, it does not react. So you have this entanglement, so to speak, where you have a feedback loop between the two reactions because one is necessary to create the active site for the other. Now, this you can put into a kinetic model, yes. And one sees, depending on the kinetics of how this is happening, the first reaction, it changes the oxidation state of nickel to nickel oxide. And the second reaction, methane reacts with nickel oxide, of course, brings it back to the metal. And you see now this opposing two trends. And everything depends now on the kinetics of how long is this oxide alive, whether you either from CO and water or from CO and hydrogen. And of course, the water has then consecutive reactions and forms by reverse water gas shift hydrogen. And this is why it's not so easy to find directly from the composition of CO and hydrogen what reaction is ongoing. But we made a model, and you see quite nicely, yeah, we can model this, okay. And the bottom line says, yes, we can use this very simplified model with these four different reaction pathways and some kinetic parameters to quite nicely describe how the reaction actually works. My last part is now we have understood all this, then we need to make some use out of this. This is also something John always wanted to make something practical out of this. He wanted to help industry to make better catalysts in order to increase industrial output. So do we. We consider now a catalyst from all of these experiments as a 3-layer system. It has a reactive interface, it has something subsurface, and it has a functional interface where the whole catalyst is stick to the support. At the reactive interface, you have restructuring and diffusion at surface diffusion. At the lower interface, you have diffusion from the support. So we saw this in some of the examples, and you have stress and strain. So these are our variables that we have in the system. Now, the best thing if you want to control this is you convert now catalysts that are made out of nanoparticles sitting in a support into a thin layer. Because if I make a thin layer out of this, you can vary the thickness, and you can, of course, almost at will change the interfaces. The functional interface can be very different than the reactive interface. It's like 1 or 2 atom layers of something on top of something else, a buffer layer, and then you can make essentially whatever you want. That's not simple, and so we build a quite complicated instrument that I show you here. This is in front of a synchrotron beam because we have, of course, to use synchrotron photo emission in order to teach us what we are doing there. This is a quite complicated thing to make such layers. And we can actually do this. Yeah, here we put silicon on, platinum on top of silicon. That was our first attempt. Of course, it miserably failed because the platinum reduced the silicon oxide and you made silicon nanowires out of this. This is beautiful for nanoscientists, but it's of course terrible for catalysis. You don't want to do that. So we did something different, and that was essentially now for the UK Catalysis Hub, because we have a collaboration where this is of relevance. We synthesized, because of you, this palladium gold system, and we wanted to see how well we can make thin layers of palladium gold. The answer here is yes, we can make them very nicely, and you see these thin films about 5 nanometers thick, and you see in atomic resolution. Our particles is a closed film. You see the 2 interfaces on your side. On your side, on the right-hand side is the functional interface, on the left-hand side is the reactive interface. Last slide of the results. Is this any good? Also, John always asks me, is this good? Does this help? Yes, it does. We use acetylene hydrogenation also because of the collaboration with the Catalysis Hub. And we found first the functional interface is not inert against hydrogen, but gold prevents this. So if you put gold in the system, it's completely stable and is stable for weeks under reaction conditions. We were surprised to find that on the thin films, gold had very little electronic effect on the thing, but it changed the morphology completely. It was absolutely nice and flat and stable. We used CO adsorption as a probe in order to find that there is no electronic effect, at least no strong one. Performance data, this is a selectivity activity plot. You see palladium nanoparticles on alumina, which is terrible, highly active, not selective. You see the technical catalyst, palladium 20 Ag80, this is the technical catalyst that we use for this reaction, is quite selective, but very inactive. Then you see these blue points, these are alloys, palladium, gallium that we did a couple of years ago. And you see the yellow data points, this is our thin film. So this is super active, enormously active. Think this is a logarithmic scale on the x-axis. So this is 90,000 times increase in activity. And we have no surface area. So there's no support, no square meters. This is just geometric area. Here you show the comparison. This is a nickel crystal in green. And these are our thin films. And one sees how even per surface area, there's about a 2-fold increase in productivity. That's interesting because it tells us we change now the kinetics of carbon diffusing into the system, because that is the actuator that changes the selectivity of the process. That comes from theory. And some people in this audience might like turnover frequencies. We determine the turnover frequency by measuring the microcalorimetric CO adsorption of the system in order to have, we don't count the atoms, but we measure them by an experiment. And then we can see with respect to fancy catalysts from the literature, like this palladium on nanodiamond, the palladium on C3 and 4, we're doing quite well with the turnover frequency. This is a good catalyst. Last slide. What do we do in catalysis science when we design something? We have to solve a problem. This is one problem with 3 variables. We want an active catalyst, we want a selective catalyst, but we want also a stable catalyst. And academic work usually focused on activity and a little bit on selectivity, but hardly ever on sustainability. That has to change for the future, because we need to be more careful with our resources. This means this is a triangle, and we have to find the optimum in the triangle. So this is, to go for any one of these parameters is probably never giving you a good solution. So catalysis encompasses the directed coupling of multiple processes of chemical dynamics. It works through temporal and dimensional entanglement. This is terrible because it's not easy to fit this. The fundamentals of catalysis were all discovered by disentangling these complicated systems. The price that was being paid is dysfunctionality. So these model systems don't usually work very well. This could have said John, but he had better words for that. The design of a catalyst requires creating knowledge by operando analysis and transform it into adapted synthesis and adapted operational concepts. And both of them are necessary because you have this chemical potential thing. So this is what you see there, what we really have to do. And this is way more difficult than optimizing any one of these blobs. This is what you do normally. You never have this systemic view on a catalyst. And this systemic view is so important. Albert Einstein said there is no fundamental law requiring simplicity. Yeah, that's a good one. John did even better. You see, he used more words. This is also very characteristic of John. And I took this quote from the paper that you mentioned. The subject of catalysis is not only an ancient lineage, but also of great current practical importance. And in view of its perennial fascination and numerous enigmatic features, it continues to stimulate many exciting, academically oriented adventures. This is a typical Sir John sentence. You can't do any better. Thanks so much for your attention.
Well, thank you very much, Robert. Absolutely fascinating talk. We have time perhaps for just a couple of quick questions. So, anyone have a question? Thomas?
Yeah, fantastic talk. Blown away. So towards the end, fantastic talk. Thank you very much. Blown away. Towards the end, the thin films are so much more active. But what about the stability?
As I say, one has to work on the stability. That is the key issue. We have now very good stability. We can work this for say a week or so, and they do not delineate anymore. But this is the design of the functional interface. So everything that we do is on what kind of surface preparation do we put our palladium. Right. And as I said, the gold is a very important part of this. So if you omit the gold, then this is not as stable.
Okay, thank you.
Great. There's one from Graham at the back.
Robert, fascinating. I was just thinking about your effect of sulfur on the silver catalyst, where you started. It's sort of much since then, but go back to where you started. And I remember that you said rhenium has a similar effect. And then on top of that, I remember that there was a massive effect when people fed NO.
Yeah.
Or made the catalyst with nitrates.
Yeah.
Is that the same type of effect?
It's all the same because the NO only has the effect, it falls into atomic oxygen much easier than O2, so it creates, in the same conditions, more subsurface oxygen, presses out more silver, more sulfur onto the silver. The key issue is you have to avoid that this crystallizes. Of course, sulfur reacts with oxygen to form sulfate, it forms silver sulfate, and this is a complete poison of the system. You have to catch it as it is being oxidized from, in the case of SO3 to SO4, only then it's active. This is called the unreconstructed sulfur reconstruction of silver. It's a very short and intermediate system, and it depends so critically on the amount of oxygen that is available. NO just reduces the necessity to have high pressures of oxygen in the gas phase.
Thanks very much.
You've explained that to me. After 40 years, I now understand it. Thank you.
Good.
Okay, well, I'm sure there'll be plenty more questions, but we probably should move on. So, no, quick.
It might be a naive question, but I'm just asking, what is the time scale of operation in Operando? Is it in the second scale because of the concentration of the intermediates? Isn't it, can you really...
Oh, that's a very complicated question. We are not very good at timescales because the turnover timescale is in the order of microseconds or something. And of course, elementary processes happen in femtoseconds. And how they are coupled, this is unknown to us. So there's a lot here next door, they're working on this, trying to find out how that's being done. But what we need to do is we need to understand that adsorption and rearrangement of the reactants at the surface have to be happening in the same time scale as the creation of these active sites. So, and that is, of course, difficult. Normally, you would expect that the nucleation is way slower than the reaction at the surface. And how that is so fast, this is something we are doing a lot of theory at the moment with Michele Parinello. He is the perfect person to do this. And since 3 years, we are collaborating with him, trying to find the exact arrangement of the timescales.
Okay, well, look, let's thank Robert again for that talk.